Hey and welcome back. I love how on this channel one thing leads to another. So we're talking about very small nuclear bombs that were exploded in the atmosphere, and they were made small and they were wrapped up with tungsten. And I didn't really know anything about it, but you guys know lots. And somebody wrote this really interesting letter. He said, Professor Simon, I worked on Ireland's strongest lighthouse that shone out into the Atlantic, and it was nuclear powered. Nuclear powered lighthouses. I hadn't heard of such a thing, and it sounds like a great idea. And he sent me a link to this film where you see them installing this tiny nuclear reactor, which was used by Trinity House and other countries to power their remote seagoing lights and lighthouses around the world. And of course, it was used in space. It seems that there is a lot of technology in micronuclear power. Let's just put my cards on the table. I'm actually a fan of nuclear power, but I'm not a fan of nuclear waste. There hasn't been a nuclear reactor built in the history of our world which has really been dismantled and cleaned up. Okay, nuclear power is carbon neutral, but the problem with nuclear waste is massive. Every nuclear reactor just stores it on site. No country has really come up with a long-term storage. And I mean, that raises a whole lot of issues. You're talking thousands of years. I always like the idea of how do you write a sign saying danger, keep out for somebody in 200,000 years? Ooh. Anyway, that could be another film. But back to today. Let's look at micro nuclear power plants. They're really interesting. I didn't know about the Lighthouse project. I had heard about nuclear reactors in space. Any probe that goes beyond Mars really isn't going to get enough solar energy with solar cells, that's my solar cells, hanging out to produce power for the craft. So all these deep space probes have some kind of nuclear reactor in them. And let's look at those today and see what we can learn, because maybe we'll have one in our basement.
NASA uses deep space science missions to explore the underlying fabric of the universe. These missions provide data on the giant gaseous planets such as Jupiter and Saturn, their moons, and other solar system objects such as asteroids and comets. These missions are vital to understanding the origins of the universe. Historically, deep space missions have relied on radioisotope power systems for energy because solar power is not practical beyond Mars. The nuclear isotope that powers these systems is plutonium-238. NASA has used plutonium-238 systems, developed in part by the Los Alamos National Laboratory, safely and reliably for over 40 years. Currently, the United States has recognized that there is a potential shortage of plutonium-238, and the Department of Energy is restarting production of this valuable isotope. To enhance NASA's exploration capabilities, Los Alamos is proposing a very small uranium-based reactor as a supplement to radioisotope power systems for some deep space missions. This will reduce the demand for plutonium-238 and allow it to be available for missions where radioisotope systems are the only practical option. The small reactor system proposed by Los Alamos is very simple and relies on many well-established technologies. The proposed reactor is made up of 6 pieces: a reactor core reflector, a rod to start the reactor, heat pipes to move energy, radiation shielding, and Stirling engines for power. The power source is a 50-pound cylinder of enriched uranium that is approximately 4 inches in diameter. A beryllium reflector that is approximately 10 inches in diameter surrounds the uranium core. The entire reactor core is about 12 inches tall. A single rod of boron carbide is used to turn the reactor on or off. The reactor uses well-established nuclear physics to self-regulate the fission reactions and eliminates the need for complicated control systems. 8 heat pipes that are embedded in the beryllium reflector remove heat produced in the reactor core. Heat pipes are passive heat removal devices that efficiently move thermal energy. Heat pipes were invented at Los Alamos in 1963. Since then, heat pipes have gone mainstream and are used in applications ranging from electronics to the Alaskan pipeline. If you own a laptop, its cooling system likely uses heat pipes. Heat pipes remove the need for complicated coolant loops and pumps in this reactor. The heat pipes connect to 8 Stirling engines that produce the electricity for the spacecraft. Stirling engines, initially developed in the 19th century, are becoming a very reliable and robust power conversion technology, particularly for low-power applications, both commercially and as part of NASA's Advanced Stirling Radioisotope Generator. The proposed small reactor could produce 500 watts of power from 8 Stirling engines weighing about 3 pounds each. A radiation shield lies between the reactor core and the Stirling engines. The shield protects the electronics in the Stirling engines, the spacecraft, and scientific instruments. This small reactor could be scaled up to more challenging applications like surface power sources on Mars or spacecraft propulsion using electrically driven ion thrusters. Scientists and engineers have always acknowledged that the future of many space missions will only be feasible with reliable and safe nuclear energy. Now is the time to take a bold step into the future.
Here's some fascinating archive from the early days of micro-nuclear reactors.
The SNAP-8 electrical generating system for spacecraft is being developed at the Atomics International Test Facility for the Atomic Energy Commission and the National Aeronautics and Space Administration. This film depicts the status of SNAP-8 component evolution and systems development through the start of reactor power testing during the summer of 1963. The nuclear system is based on the proven SNAP-2 concept. The nuclear reactor is uranium zirconium hydride, fueled and moderated, and NAC-cooled. The SNAP-8 reactor is designed to deliver up to 600 kilowatts of usable thermal power. The entire SNAP-8 electrical generating system is comprised of the nuclear system and the power conversion system. The nuclear system consists of the reactor core structure, controls, safety devices, and shield. The reactor heat is transferred to a mercury boiler through a closed-loop NAC coolant system. The resulting mercury vapor drives a turbo alternator, which generates 35 kilowatts of net electric power. The mercury vapor is condensed in a heat exchanger, and the liquid mercury is returned then to the boiler. The condenser is cooled by an independent NAC heat transfer loop, which dissipates the waste heat to space. A fourth organic lubricant cooling loop is employed to furnish cooled lubricant to bearings and coolant to heat-sensitive components in the system. All nuclear system operational controls will be contained in the electrical generating system package. Except for the telemetered startup signal, the system is designed to be independent of spacecraft systems. The reactor operates in a 3-foot diameter steel containment vessel enclosing a helium atmosphere, a measure calculated to retard oxidation of the beryllium reflector. A 4-foot thick concrete shutdown shield is placed between the reactor and the control drum actuators so that actuators and position indicators may be serviced. The reactor heat is transferred from a shielded and contained NAC primary loop through an intermediate heat exchanger to a secondary non-radioactive NAC system, which in turn dissipates the reactor heat to the atmosphere. A removable clean room is placed over the containment vessel prior to reactor core installation. The core was fully assembled in a critical facility adjacent to the S8ER test building. Neutron-absorbing rods were inserted, and the entire unitized core was safely transported to and loaded into the containment vessel. The first of the program series of the SNAP-8 nuclear power tests started in mid-1963.
I also love this. This is some footage of nuclear reactors underwater starting up. The blue glow, which is very distinctive of nuclear reactors, is caused by energetic particles, electrons probably, traveling faster than the speed of light. I don't understand that. Anyway, they do. And they actually, produce this blue color, which is very distinctive of a reactor starting up. It's beautiful, but also looks really deadly. Look how fast it propagates. Enjoy this. Hey, that was new to me, probably not new to you, so please leave your erudite, smart comments, only, in the comment box below. Consider supporting the channel, tell your mates, remember if you subscribe and ring the bell, that's my bell icon, that it's free. This channel certainly needs a bigger audience. The films are doing great, but they need to be bigger to be a bit more self-sustaining. And consider supporting me on Patreon and Wallace the Goat. Thanks for watching, and as always, because of you, the truth is out there.